Welcome back to pattern recognition. So today we want to look a bit more into the logistic regression, and in particular we are interested in how to estimate the actual regression parameters, so the decision boundaries. So today we look more into logistic regression, and until now we have seen that our f of x was some arbitrary function, and we've seen, for example, that it could be formulated as a quadratic function, as we've seen with the Gaussian distributions. So generally we can express as a nonlinear function, and the idea that we want to use now is to linearize our estimation, and what we will do is we will map our function into a higher dimensional space. So if you consider, for example, the quadratic function, then we can see that we can express it component-wise in the following way. So we know x is a vector consisting of x1 and x2. A can be written down in terms of the individual components, and the same is also true for alpha. And if you look for the component-wise notation, you see that f of x can be written out in components, and we observe that the components that we have in there, they are linear. So all the components of a and alpha are linear in this equation, and the x's and so on, they appear in quadratic and linear terms. So this means that we can rewrite this into a function of x with some x prime, where x prime is lifted to a 6-dimensional space. So x prime is now rewritten from x1, x2 to x1 to the power of 2, x1, x2, x2 to the power of 2, x1, x2, and 1. And if we do that, then we can rewrite the entire equation into an inner product of our parameters. And the parameter vector is now a11, a12 plus a21, a22, alpha 1, alpha 2, and alpha 0. So this is a kind of interesting observation, because it allows us to bring our nonlinear quadratic function into a linear combination that is linear in the parameters that we wish to estimate. And this is a pretty cool observation, because if we use this now, we can essentially map nonlinear functions into a higher dimensionality, and in this higher dimensionality we are still linear with respect to the parameters. So we can now remember our logistic function, and we can see that if we use this trick, then we can essentially take our logistic function and apply it in this high dimensional parameter space, and we don't have to touch the logistic function. All that we have to do is we have to map essentially the axis into a higher dimensional space, but we can then use, instead of the version where we were using the f of x, which could be a general nonlinear function, we can replace it now with our parameter vector theta, and we essentially have the theta transpose x, which is a linear decision boundary but in a higher dimensional space. And we can now use this and explore this idea a little further. So also we want to assume the posteriors to be given by two classes. So we have the class y equals 0 and y equals 1. If we do so, we can write down the probabilities of the posteriors as 1 minus g of theta transpose x and g theta transpose x, where we essentially reuse our logistic function or sigmoid function, and the thing we are interested in now is the parameter vector theta. So somehow we have to estimate theta from a set of m training observations. And you remember we are in the case of supervised learning here, so we have some set S, which is our training data set, and it contains m samples, and they are essentially coupled observations where we have some x1, y1, and more of these tuples up to m. Now the method of choice is the maximum likelihood estimation. If we want to use that, then let's look a bit into the formulation, how we want to write the posteriors, and we can rewrite this as a Bernoulli probability. So the probability of y given x can be rewritten using our logistic functions, and now we use the logistic function to the power of y, or if we are in the other case, then it's going to be 1 minus the logistic function to the power of 1 minus y. And you remember we had our y essentially either 0 or 1, and in this particular choice we can now see that our probability, depending on which class we are actually having in the ground truth, will either choose the one or the other one. Because if you take something to the power of 0, then it will simply return 1 and the respective term will cancel out. So this kind of notation is very beneficial. Now let's go ahead and look into the log likelihood function, and we can write up the log likelihood function as the logarithm of our general probability, and we assume that all of the training samples are mutually independent, so we can simply then write this up as a product over all the posterior probabilities. This is kind of useful because if we now apply the logarithm, then we see that the maximum of this function does not change, and still we can reformulate it. Our product turns into a sum, and then we can also pull the logarithm inside, which is actually converting our product into the sum, and then we see it's a sum over logarithms, and within the bracket we see the definition of our posterior probability, and this is again the formulation using the Bernoulli probability as mentioned previously. So here we have these terms with the logistic function. Now we can go ahead and use the property of the logarithm, where we then can pull the exponents in front of the logarithm, and then we get essentially the following observation in this line, that all of the exponents have been moved in front of the logarithm. Also, we are breaking up the two terms of the sigmoid functions into a sum because they were a product, and then I can always convert a product within the logarithm as a sum of two logarithms, as we did previously. This is already a first step towards simplifying this, but we can see that this can be simplified further, and in the next step we actually want to use the definition of the sigmoid or logistic function, and you can see that the left hand term we can essentially rewrite using the exponential function here, and instead of using the notation with the negative sign, you can see that we already expanded the fraction on the left hand side by adding the exponential term also to the numerator. So this brings us then into a kind of notation that is very similar to what we see in the second term, where we have the logistic function in the formulation 1 minus g of theta inner product x, and this can also then be reformulated here on the right hand side as 1 over 1 plus e to the power of theta inner product xi. You see now why we did the adaptation on the left hand side. They both now have the same denominator. Now with this we can simplify this further. You can see now that in the first term we essentially see that we have the e to the power of theta inner product xi, and if I apply the logarithm to this, then only yi theta inner product xi remains, and on the right hand side then I still have some term that I could not get rid of, where we still have the logistic function in there. But you can see that if I look closely, we essentially have again the same formulation as previously, so we can move it back to the logistic function and we get the logarithm of 1 minus logistic function theta inner product xi. So this is already a simplification, and now you can see with this particular log likelihood function, I have two further observations that I want to actually hint you at. What you can see here is essentially that the negative of the log likelihood function will return the cross entropy of y and the logistic function of theta transpose x. And also note that the negative of the log likelihood function here is a convex function. So this is a very nice property, and we will use that in the following. So in the next video, we will talk about how to actually find the point of optimality and how to determine those parameters. So now we've seen the log likelihood function, so we've seen which optimization problem we want to solve, and this optimization problem will be solved in the next video. So thank you very much for listening, and looking forward to seeing you in the next video.